To conclude Lab 2, we used two different methods to solve the same circuit. In Activity 1, we broke the circuit down into 3 different loops and used Ohm's law in combination with Kirchhoff's voltage and current law to solve for the unknown values. We ended up with 6 unknown currents and used the matrix to solve for those currents and then use those values to solve for any other unknowns. In Activity 2, we used the superposition theorem to break the circuit down into 2 simpler circuits. And in those simpler circuits, it was the same circuit, but just one voltage source being short-circuited. Then we used node voltage analysis on the extraordinary nodes of those simpler circuits to solve for the currents. We did that by using Ohm's law and Kirchhoff's voltage and current laws again. So for activities 1 and 2, we obtained the same values, which proves that you can solve or analyze the circuit with different methods and still get the same results. And we also concluded that in whichever method that you use, the same 3 basic laws are going to be applied to those methods. And those laws are Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. So in the end, you can pick any method you want to solve a circuit as long as you do it correctly, and ultimately the choice is up to whatever the person who's solving the circuit prefers. That's all for group 5. Thank you.
Hello, my name is SanchezLucero. My Panther ID is 6115497. This is group 5, working on LabActivity 2 for the course EEL3110C.
Hello, my name is Sergio Gomez. My Panther ID is 2832878. During Lab 2, we are going to be working with Kirchhoff voltage and current laws, along with superposition, and using Ohm's law, we're going to be determining power across a particular resistor in one circuit that we set up. And then there's going to be 2 separate assignments within this lab, and we will discuss each of them momentarily. So for activity 1, we were supposed to set up a simple circuit. It's presented on the screen now. There were some conditions required. So R1 was supposed to be greater than or equal to 1 kilo ohm. So we set R1 to equal to 1 kilo ohm. R2 is supposed to be greater than or equal to R1. So we set R1 equal to R2. R3 was supposed to be between 2.2 kilo ohms and 10 kilo ohms. So we decided for simplicity's sake to leave it at 5 kilo ohms. R4 was supposed to be between 470 ohms and 100 kilo ohms. We decided to set it up at 5 kilo ohms. With this entire circuit, we also went ahead and set voltage 1 equal to 5 volts and voltage 2 equal to 5 volts, meeting all of the conditions required for activity 1. After that was completed, if you look onto the screen, you'll see that we went ahead and set up each of the nodes. So we have node 1 where we have IX going in, I1 going out, that's going to resistor 1, and then I4 going towards resistor 4. Node 2 is in the center of the screen. We have I1 going in, and we have I2 going out and I3 going out. And then over to node 3, we have I2 going in, I4 going in, and IY going in, just for representation purposes. So that considers the 3 nodes. Now, as for our loops, and I'll go over each of these equations. We have loop 1 is equal, starting over here at voltage, we have -5 plus I1 R1 plus I3 R3, and that's all equal to 0. Loop 2, we go minus I3 R3, so that's right here for the resistor, plus I2 R2 plus 5. That's for the voltage there, and that's equal to 0. And then loop 3 is the upper loop. So we have and we start right here at node 2, going clockwise. So we have -1 R1 plus I4 R4 minus I2 R2 is equal to 0. So that constitutes our 6 equations. And then those 6 equations are going to provide us the solutions to our 6 unknowns. Our 6 unknowns are I1, I2, I3, I4, IX, and IY. And then I'm going to go ahead and show you the calculations we did. We went ahead and set them up into a matrix. Let's see if I can get this right. So these are the, there we go. So these are the, this is the matrix set up in the appropriate form. That is I1, I2, I3, I4, IX, IY is equal to our voltage. And we set those up so that we could manipulate this with RREF. So 1050005 all the way down. We ended up mathematically with I1 equaling 454.55 microamps, I2 equaling negative 454.55 microamps, I3 equaling 909.09 microamps, I4 equaling 0 amps, IX equaling 454.55 microamps, and then IY equaling 454.55 microamps. The power going through, or power absorbed by R3 is going to be, well, power is equal to I squared times R. Now that we have the I in that area, that is I3. So we have 909.09 e to the negative 6 amps squared times 5 e to the 3 ohms, bringing our power to P is equal to 0.004132 watts. And that is the power going through R3. And that, now, in terms of what we have here, since we have two equivalent voltages in loop 1 and loop 2, they almost effectively kind of cancel each other out. None of the amperage is being consumed through R4, which we found to be interesting, but it kind of makes sense when you realize that everything's being consumed by this side of the equation, especially through loop 1 and loop 2. So it makes sense that loop 3 isn't gonna have a massive impact, because most of our current is being consumed by R1, R2, and R3. Primarily R3 being the biggest one. And that concludes activity number 1. Going back to activity 1, I forgot to actually show the circuit as set up with all the probes on multi-sim. As you can see, we have R1, R2, R3, and R4, 1 kilo ohm, 1 kilo ohm, 5 kilo ohms, and 5 kilo ohms, respectively, with a voltage 1 of 5 volts and a voltage 2 of 5 volts. As is visible here, we have 454 microamps. For I1, we have negative 454 microamps. For I2, we have 909 microamps for I3, and then we have 0 amps going for I4, as is expected. So it all ends up working out accordingly.
So for activity 2, we're using the superposition theorem to analyze the circuit. It's just another method of analyzing the circuit, which you can use in addition to the Kirchhoff's voltage and current laws. So for the superposition theorem, since we have 2 voltage sources, what you want to do is short circuit one of them, essentially setting it equal to 0. And then
you show the screen?
Oh, sorry. Oh, I forgot, because I could see it online. Okay. Should I start over?
No, I just keep going.
Okay, so now that you guys can actually see the circuit, we short-circuited voltage source 2 and kept voltage source 1 the same, and we're just analyzing the circuit here. So what you want to do is find the negative terminal of the voltage source and set that node equal to the ground. That way, all of these nodes are also equal to 0 volts. Then you want to find your extraordinary nodes, which are the ones that are connected to 3 elements. So here I have 1 extraordinary node. This one's connected to the voltage source, resistor 1, and resistor 4. This node is unknown. The voltage at this node is known, which is 5 volts. Here in this extraordinary node, we're connected to resistor 1, resistor 3, and resistor 2. And we want to set the circuit sorry, not the circuits, the currents coming out of the node for convenience. And then, so in order to find the values of the currents, we're going to use Kirchhoff's current law. So here, all of the currents are coming out, they all equal to 0. Then you want to put them in terms of voltage and resistance. So we use the difference in the voltages divided by the resistance. And that will lead you to solving for the voltage at that node, which is 2.273 volts. Then we use the voltage to solve for the current. And we get these values here. If we look on multisim, we can see the same value. Let me run it to make sure. So here we have the same values. Here would be the short circuit for voltage source 2. Then we want to short circuit voltage source 1 and solve everything for V2. Since they have the same values, the only thing that would change would be current 2 and current 1 would be swapped with the values from this first circuit. So you go through the same process and you get almost the same numbers. Then you want to add up all the values you got. So for the currents, you add up the current you got for this circuit and the current you got for this circuit. You end up with negative 454 microamps for current 1. For current 2, you get negative 454 microamps as well. And negative just means that instead of these currents coming out of the node, they're actually going into it. For current 3, we have 909.2 microamps coming out of the node. And as mentioned in activity 1, the current 4 is 0 amps because they cancel each other out. And for current X and current Y, we have 454 microamps. And the voltage at the node, which you get from adding up what you got from the superposition theorem, is 4.546 volts. So if we look at this circuit at multisim, you can see that all the values match up here. And you can use those same values to solve for the power absorbed by resistor 3, which would give you the same value as activity 1. That's it.
To conclude Lab 2, we used 2 different methods to solve the same circuit. In activity 1, we broke the circuit down into 3 different loops and used Ohm's law in combination with Kirchhoff's voltage and current law to solve for the unknown values. We ended up with 6 unknown currents and used the matrix to solve for those currents and then use those values to solve for any other unknowns. In activity 2, we used the superposition theorem to break the circuit down into 2 simpler circuits. And in those simpler circuits, it was the same circuit, but just one voltage source being short circuited. Then we used node voltage analysis on the extraordinary nodes of those simpler circuits to solve for the currents. We did that by using Ohm's law and Kirchhoff's voltage and current laws again. So for activities 1 and 2, we obtained the same values, which proves that you can solve or analyze the circuit with different methods and still get the same results. And we also concluded that in whichever method that you use, the same 3 basic laws are going to be applied to those methods. And those laws are Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. So in the end, you can pick any method you want to solve a circuit as long as you do it correctly, and ultimately the choice is up to whatever the person who's solving the circuit prefers. That's all for group 5. Thank you.